Hello, this is Mr. Collier, and today we're doing derivatives of exponentials, logs, and trig functions. Okay, so let's check out this first derivative on the calculator. So we need to go to function. We can type in the function into F1, and then to graph its derivative in here. Let me just show you how to do that. So let's go to click on this button, click on this derivative thing here. Here you can just simply type in F and F1, just make it look like that. F1 bracket with an X in there. It'll find the derivative of the function in F1. Okay, so we have that in there. Let's go to shift plot and make sure it's set up from -10 to 10. And then when we go to plot, we can see it right there. And then indicating any key features, those are maximums and minimums, maybe points of intersection. So you can get the maximum and minimum using extremum. Okay, and then you can get this one by going to function extremum. Okay, so you can get those, get the points of intersection by going to intersection, and yeah, you can find those, and then you can graph it like this, indicating some of the key features. Okay, so you can do the same thing for e to the x. Let's do that. So you just need to change this function. Let's just delete the whole thing. Then we can type in e to the x. So let's find e. There's e, and then let's do e to the x. I'll go to plot, and actually get the same thing there. Let me show you what happens. We can actually turn off F1 so we can just see F2, the derivative. And you can see it was just behind the blue one the whole time, because the derivative of e to the x is just e to the x. So they're both the same thing. Okay, just like any exponential, it goes through the point 0, 1, by the way. Okay, so that's the graph of y equals e to the x, and the derivative of that function is also e to the x. Okay, let's look at ln x, and let me go and put this back on, change this to ln x. And okay, so the original function is here, okay, in blue, and then the derivative is in red here. Okay, so technically this part shouldn't be here because the blue one's only defined from x greater than 0, so the derivative should also be just greater than, or greater than 0. Anyway, let's graph that. So this is f of x equals ln x, and here we have f prime of x equals 1 over x. I guess we could say for x greater than 0. Okay, so now we have, just from those graphs from before, we can see that f prime of x equals e to the power of x. We can prove that later once we know more calculus. And the second one we can prove pretty soon, just given the fact that we know the first one. So we'll prove that one a bit later. So the derivative of ln x is 1 over x. Okay, so we can find this derivative. Now you can use your log rules to help you out as well, and your exponent rules. Just rewrite the function as 2 ln x plus, we can bring the exponent down to 2 ln x, and we can write this as e to the 4 times e to the x, or we don't really need that one. So then we get the derivative, dy dx equals, it's going to be 2 times 1 over x plus also 2 times 1 over x, so I guess we could have combined those before. And this is just a constant, and the derivative of e to the x is e to the x, so that's going to be the same. So actually we could just rewrite that same there like that. So this is 2 over x plus 2 over x is 4 over x. So this is the derivative of this function. Okay, so let's take a look at this one here. Let's see, the easiest way to do this is probably rewriting this with the log rule. We can write this as ln x over ln 2, right? And that's like 1 over ln 2 times ln x. So we find the derivative is 1 over ln 2 times 1 over x, so it's 1 over x ln 2. So that is simply the derivative right there. Alright, next let's look at sine. This is a sine function right here. Now we can see the derivative here at pi over 2, the slope of the tangent is 0. At pi, we're looking at -1. At 3 pi over 2, we're looking at 0 again. Then here it's 1 again, so it keeps going like that. And you might notice these are exactly the same values for cosine. So if f of x is sine x, then f prime of x equals cosine x. And similarly, if, let's say, g of x is cosine x, you can use the same logic to show that g prime of x is negative sine x. Okay, we'll be able to prove those much later, though. Okay, so we just talked about that part. Also, the derivative of tangent, we'll be able to prove this pretty soon, is secant squared. We'll be able to prove that a bit later. So find the, let's look at this one here. Find the derivative and the gradient of the curve when x equals pi over 6. So we just find the derivative. And that's going to be 2 cosine x. Derivative of cosine is negative sine, so it's going to be -3 sine x. And tangent is secant squared. Okay, so if we want to evaluate it at pi over 6, then we just substitute that in. I'm going to write this as cosine, 1 over cosine pi over 6 squared. So let's draw a right triangle with pi over 6, and this is 1, 2, 3. So cosine pi over 6 is root 3 over 2. And sine pi over 6 is half. And cosine pi over 6 we saw was that, so it's 1 over root 3 over 2 squared. So I'm going to simplify that over here now. That's going to be root 3 minus 3 over 2 minus, it's going to be 1 over 3 over 4, so it's minus 4 thirds. So we get a common denominator of 6, and we have 6 root 3 minus 9 minus 8 over 6, which is 6 root 3 minus 17 over 6 is the derivative there. Okay, let's take a look at another one. We're not going to do all these together, but so tangent touches at one point a normal. This is a normal. So if you got a function like this, this is the tangent. The normal is perpendicular to the tangent. Normal is perpendicular to the tangent. So let's take a look at an example. Find the equation of the tangent at x equals 1 to this curve. Okay, so let's do that. Let's just take a look at the formula booklet for a second. Okay, so in the formula booklet, let's take a look at the calculus section. This is the IB formula booklet. So we have a formula here for it, and we can easily see the formula if you just rewrite this in terms of ln using the change of base formula. But it's 1 over x ln a, where a is the base, right? So the derivative is going to be 1 over x ln 2. And to get the equation of the tangent, we need the slope of the tangent. So slope at that point where x equals 1 is going to be, well, 1 over 1 times ln 2, or just 1 over ln 2, right? So that's the slope at that point. To get the equation, we're going to need the y value at that point. So we use the original function to get the y value. Y equals log base 2 of 1. Okay. Log base 2 of 1, and log of any base of 1 equals 0. So that's the y value at that point. So the point we're talking about on the curve is 1 over ln 2 comma 0. Okay, so now we can get the equation of the line using point slope form. Y minus y1 equals m times x minus x1, right? So that's y minus 0 equals m, which is 1 over ln 2 times x minus 1. So it's just y equals ln 2. We could leave it like that, I suppose. The y-intercept is negative 1 over ln 2. Okay, so that's how we do that one. Let's take a look at the next one with cosecant. Okay, so let's get the slope of cosecant. So in other words, get the derivative. Cosecant, let's take a look at the formula book. The derivative of cosecant is negative cosecant cotangent. Okay, so we have, that's the derivative. And so the slope at that point is going to be negative. Let's rewrite this as 1 over sine pi over 2 times cosine. So cotangent is, tangent is sine over cosine, so cotangent is cosine over sine. So cosine pi over 2 over sine pi over 2. Okay, so that's negative 1 over sine pi over 2. That's 0, 1, so sine is 1. And cosine pi over 2, though, is 0. So the whole thing is 0. Okay, so discuss the implications of the result. The tangent at x equals pi over 2 is horizontal, I suppose you could say. Okay, let's take a look at another example here. Let's actually go over here to number 7. At what point will you get a slope of 21? So we need to find the derivative. Okay, so 2 to the power of t, let's look at the formula booklet. A to the power of x is a to the power of x ln a. Okay, so that's going to be 2 to the power of t times ln 2. Derivative of constant is 0, so we're done with that. So when we have a slope of 21, we just set the derivative equal to 21, and we can solve for t. So we have 21 over ln 2 equals 2 to the power of t. So we get t equals, well, let's log both sides, natural log. That's probably the best thing to do. Let's rewrite that. Natural log of 21 over ln 2 equals t ln 2. So t equals 1 over ln 2 times ln 21 over ln 2. Okay, and that works out to be 4.92 if you do that in the calculator. Okay, we need to have the y value of the point as well. So the y value is just simply 2 to the power of that. You can type that into your calculator, copy and paste to get the exact value. So that's 27.3. So the point is 4.92 comma 27.3. Okay, in the next example, we're going to do this one. Find the equation of the tangent to the curve at y equals secant x, where x equals this. So let's get the derivative. Secant x, we'll prove that one later, but that's secant x tan x. So let's get the slope at that point. We do 1 over cosine 7 pi over 6 times tangent 7 pi over 6. Okay, 7 pi over 6 is in this quadrant. And let's draw the pi over 6 triangle again. 1, 2, root 3. Alright, so the slope, so cosine there is going to be negative. So we're going to have negative, and the cosine is root 3 over 2. And the tangent here is 1 over root 3. Okay, when we multiply that, the root 3's cancel. So it's just going to be 1 over negative half. No, they don't cancel, they become 3, sorry. This becomes negative 2/3. Okay, so we have the slope at that point. We, of course, need the y value at that point. So we substitute into the equation secant x. So secant 7 pi over 6, which we already worked out over here. It's negative 3 over 2. Okay, so the equation of this line is going to be y plus, so that's root 3 over 2. Root 3 over 2 equals slope, which is negative 2/3, times x minus this.